One of the earliest questions has always been, what is matter around us made out of? What is its structure? What is its nature? If we look back way back into history, some of the first people to tackle this question were the Greek philosophers. Now, philosophers were deep thinkers. And their work occurred many, many years before the advent of anything that we would call science. They were not experimenters. They didn't have the scientific method. They simply observed, thought, constructed arguments to explain things, debated with each other to come up with some of their ideas. But the idea of testing their ideas and gathering data wasn't something that occurred to them, and of course their technology was extremely limited. Now, there was a prevailing idea at the time that was put forth by a Greek philosopher you've probably heard of named Aristotle and Socrates, that matter was infinitely dividable. That meant that if you took a small particle of something that they believed was pure, like gold, and you cut it in half, and then you cut it in half again, you kept cutting. They believed that you could just do that forever. As long as you could actually somehow see it and cut it in half, you would completely be able to divide it forever. Okay? Some of the early philosophers also believed in the four elements theory. Sometimes we see the description of a fifth element. Okay? And that would be earth, air, fire, water. So what's the fifth one? That would be spirit. Or sometimes you see it called the void. Okay? Some of them believed that everything around us was some combination of these four or sometimes five elements. So living things would contain this spirit, this fifth element. So for example, a cloud would be made out of air and water. Okay? The cloud floats around in the air, and occasionally water comes out, so that sort of makes sense. And trees are made out of earth and fire. They grew out of the earth, and they could burn. They could produce fire. So these were some of the ideas that were very, very common back in those days. However, if we take a look, there's one particular philosopher whose ideas were a little bit different. His name was Democritus. And what was unusual about his idea is that he thought that matter could only be divided to a certain point. Okay, that means you could divide it until you got down to this point where you would have a small, what he called fundamental particle. So eventually you'd reach this, and he decided to call these particles, his idea, to call them atomos. Okay, this is a Greek word. The letter A means not, and the Greek root tomos means cuttable. So the word atomos literally means not cuttable. So Democritus believed that everything around us was something you divided it down, was actually made out of these teeny tiny, indestructible, uncuttable particles that he called atomos. However, this idea was not particularly popular. Aristotle didn't believe in it. Aristotle was a highly influential Greek philosopher. And Aristotle suggested that the reason that this was not right was because nothing in this particle explained, well, how did these particles stay close to each other and stay together? and Democritus didn't have any answer. So Democritus's theory wasn't very well accepted. However, he wrote it down along all those other readings, a lot of his other writings, and eventually time went by. Okay, so we go through the Renaissance, we go through the Industrial Revolution, okay, we get into the we start seeing the development of the scientific method, and we start seeing some of the early chemists start to rise up. Isaac Newton, Maxwell. And then we run across a man named John Dalton. Okay, John Dalton published some of his work in the 1860s, and what he did was he read about a man named Antoine Lavoisier. Antoine Lavoisier was a French scientist who actually developed the law, should put that in there, law of conservation of mass. The law of conservation of mass says that matter is not created or destroyed in chemical reactions. Okay. He also read about Democritus's atomos. Okay. And Dalton, as he put these two ideas together, created what are called his postulates of the atom, and our first early actual model of what the atom looked like. Okay, now look at how much time, almost 4,000 years, passed between Democritus's writings and Dalton's current model. Okay, so Dalton basically came up with what are called the four postulates of the atom. Okay, his first one was that matter was composed of particles called atoms. Okay. Secondly, he said that atoms cannot be created or destroyed in chemical reactions. Okay. Next, he addressed the idea of the elements. Now, when Dalton published his work, there were probably between about 40 to 50 elements that had been identified. You know, when Democritus wrote his theories, people weren't even sure exactly what an element was. Okay, there were 4 of them. Maybe, who knows? So a lot have changed. Okay? So when Dalton wrote about elements, there were a lot of different ones. And so he applied his idea of the atom to the idea now we had a lot of 40 or 50 different possible elements. What he said was that atoms of an element are identical to each other, but different from atoms of other elements. So Dalton wasn't sure exactly how did they differ. He had some possible ideas. Maybe they were different sizes, different colors, different shapes even, but he wasn't exactly sure. He just knew that they had to be particles, that particles of particular elements had to be similar to each other. Okay, and the last one, he said that atoms were combined in compounds in fixed ratios. So for example, if a compound was made out of hydrogen and oxygen, the hydrogen and oxygen atoms were in a particular ratio. If they were in different ratios, they would make different compounds. So these are Dalton's four postulates of the atom. And what this left was for Dalton's model. Okay, so how could he draw a picture of the atom in a way that would kind of explain what he was trying to describe? Dalton basically described his model like a ball. His model is called the solid sphere. Okay? It's a sphere, it's not a circle because it's three-dimensional, and I'm not a very good artist, and so that's my three-dimensional ball. Didn't have any parts, okay? And it was indestructible. Couldn't be created or destroyed. So that's Dalton's model. Okay, so Dalton's model lasted for a little while until 1897 and a man named J.J. Thomson. Okay, Thomson was studying an interesting device. The device is called a cathode ray tube. Now, Thomson was actually not intending to study matter. Thomson was actually wanting to study electricity. Okay, a little bit was known about electricity at this point in time. Benjamin Franklin was one of the earlier studies of electricity. And Franklin had determined that electricity was made of two kinds of charges. He decided to call them positive and negative. These are just terms that he used, okay? And opposite charges attracted each other. And charges that had the same charge repelled each other. Okay, so this is a little bit of information that was already known about electricity. Now, Thomson was studying a device called the cathode ray tube. This is an interesting device because in this device, I'll show you a picture in just a minute, what we see is this device is a glass tube that has most of the air evacuated or sucked out. So sometimes we call these vacuum tubes. And there was an electrode in each end, and electrical current was applied to one side. Okay? And inside the tube, there was a little slit on one end, okay? And when they applied it, there was a little ray of something that came out and went from one electrode to the other electrode. The only way they could see it, though, was they had to put a piece of paper or something that had like what they call phosphorescent paint. This is glow-in-the-dark paint. It's like if you see t-shirts or things in makeup and stuff, you put it under a light and then you turn off the light and it kind of glows dimly. Cathode ray tubes have the same kind of stuff applied. So when the energy, say, when the ray passes in front of it, okay, the paint absorbs the energy and releases it back in light, so you can actually see it. So let's take a really quick look at this cathode ray tube here. Okay, so here's a picture of it. Okay, this end is called the cathode, and this end is called the anode. These are the two electrodes. Okay, and here's this little clip. This would be attached like a battery or some other power source. Okay, and when you hook everything up, you see this little glowing thing here. See, here's an actual picture. This is a photograph down here. You see this little glowing line. People were fascinated with what this was. What is this ray or radiation? So Thomson was studying it. Thomson had an idea after a while. He said that he wondered where the ray was coming from. He thought it might be coming out of the little pieces of metal that was used to make the cathode. Okay. And what he decided to do, now by this time people knew a little bit about the relationship between magnetism and electricity. So for example, people knew that if you took things that were that magnets could interact with electrical fields, and magnets could also influence matter in some way. So what Thomson did is Thomson took first he took a magnet and he held the magnet next to the tube to see what would happen. And lo and behold, the tube would bend. The tube would bend, the ray would actually bend in the direction of one end of the magnet. And if you flip the magnet over, I don't have a picture for that, then the ray would bend away from it. Then he set up a very, very similar experiment where he took electrical plates that could run electrical fields. So you could have a negative field and a positive field. And this time the ray would bend in the direction of the positive field and it would bend away from the negative field. So what Thomson was able to figure out from this was that whatever the cathode rays were, number one, they were matter. Because if they weren't made out of matter, then the magnet wouldn't have any effect. And they had negative charge. It's a V, negative charge. So this is really unusual. I wondered what the heck it was. What he concluded, he worked with another man named Robert Millikan. They were able to figure out a little bit more about it, and eventually they were able to figure out that whatever the rays were made of, it was incredibly small, smaller than any atom that was known. So Thomson decided that the cathode rays were a stream of tiny negatively charged particles. And that somehow they were coming out of the metal electrode on the end. So he did lots of different things. He changed the electrode, made it out of many different types of metals. Still got the exact same results. He decided to call these particles electrons. The word electron literally means electrical particle. They were smaller than any atom that was known, so they had to be a part of the atom. So they had to be coming out somehow. We hooked up the electrical current that pushed the electrons out of the atom, and they came out in this little tiny ray. So Thomson's model he decided to call this the plum pudding because it looked like plum pudding. Now I'm betting that probably most of you do not know what plum pudding looks like. Well, since we're not familiar with a plum pudding, here in America we call it the chocolate chip cookie model. Okay, now you're like, okay, I know what a chocolate chip cookie looks like. Well, plum pudding is kind of the same way, except a pudding in Great Britain, because Thomson was a British scientist, is more of a cake that's boiled so that it's very moist and very heavy and rich, and the plums are like fruit that was put into the cake. So it's like a fruit cake. So what do we have here? So imagine a ball, okay? I call this, a better word for us is chocolate chip cookie dough model. Okay, so here's our ball. This sort of looks like Dalton's model, but now it has to change. Okay, models have to change when new evidence says the models are incorrect. Models have to change and to take into account new evidence that says that they might be different. Okay, so here's our ball, like Dalton's original ball, but this isn't a solid ball. This has scattered through it all over, because Thomson believed they were probably everywhere inside the atom, little tiny negatively charged particles that he called the electrons. Okay, now, these are like chocolate chips in the cookie dough. However, they're like mini chocolate chips because the electrons are very, very, very small compared to the rest of the atom. So the question is, next he said, well, what's the rest of the atom made out of? What's the dough? Well, he said the dough had positive charge and the mass of the atom. Well, it had the mass because electrons are incredibly tiny. So the fact that if the atom had it was heavy, had to come from the dough. Now, why he said positive charge? Well, because negative and positive charges attracted to each other, and they also tend to cancel each other out because the overall charge on an atom is neutral. The overall means there's no charge overall. So he figured out if there was negative charge in the atom, well, there had to be some positive charge to balance it out too. Okay, so that was a really exciting model. People were very, very interested in it, and they said, wow, okay, so it turns out Dalton was wrong. The atom is not uncuttable. The atom actually had little parts, little bits that we can push out with electrical charge called electrons. Well, unfortunately, Thomson's interesting model didn't last very long because Thomson had a student. Thomson's student's name was Ernest Rutherford. And like all good students, he wanted to test to see if his teacher was really right. Now, he was a grown man, not a teenager. But what he decided to do was he decided to set up an experiment to try to figure out some more about these electrons and figure out, well, maybe exactly where they were. And a little bit more about, well, what was the dough made out of? That's what he really wanted to know. What was this positive charge? Was it another particle? What was it exactly? So Rutherford decided to use something that were called alpha particles. Alpha particles are a form of radioactivity. Now, radioactivity had been discovered, and not a whole lot was known about exactly what the radioactivity was made out of. But for alpha particles, we knew two things. They were large and positively charged. They were they weren't bigger than a lot of them. They looked to be about the same size, pretty close to the size of helium, but they were positively charged, and helium is a neutral atom. Okay, so what they decided to do was they decided to basically take a really, really, really thin layer of something. It chose gold because gold can be pounded, so it's only a few atoms thick. And they decided to basically point alpha particles and let alpha particles strike the gold foil. So let's look at this. This is Rutherford's gold foil experiment. This is called an alpha particle emitter. This would just be a lump of a radioactive substance that would give off alpha particles, and there would be a little hole in one side, so that even though alpha particles are coming off in every direction, they would only be able to escape the box through the hole. So he could point the alpha particle to whatever he wanted. Here's the gold foil. The gold foil is super, super, super thin. Now, he wanted to see what would happen when the alpha particles hit the gold foil. Now, the problem is that alpha particles are basically invisible to the naked eye. So he took a screen and he put the same kind of phosphorescent paint as we see in a cathode ray, so you get a little dot of light every time he could see the alpha particle hit. Now, what he expected to see was most of the alpha particles should go right through. And some of them, though, ended up being deflected off at pretty big angles, and then there were these really weird, unexpected results, where some of the alpha particles looked like they bounced off the gold foil. Now this is really unusual. Now it was only very few of them. Most of them went this way, a couple of them went here, and just every once in a while you get this. So Rutherford had to come up with a different model, because nothing about the chocolate chip cookie explained this particular experimental results. So what Rutherford said, he said there has to be something that's really, really dense and positively charged somewhere in the atom, because it has to be dense enough, in other words, heavy enough, and positively charged so that it pushes away the alpha particle. That's where this bouncing off is coming from. Okay, and so what he said is that some of the particles were getting close to whatever this thing was, okay, and so they got kind of deflected off of their path, like an asteroid coming close to the gravitational field of Earth or something. But it had to be really small, because only some of them got deflected, and only some of them seemed to strike it dead on. So he posited that it also had to be extremely small. Well, what would that look like? And what would you call it? Well, he figured it was small, and it was also in the very, very center. So Rutherford decided to call whatever this dense, positively charged small thing in the middle of an atom, he called it the nucleus. Nucleus means center. So let's look at what Rutherford's model would look like. How does he put all this together? Sorry, can't write. Rutherford's model is sometimes called the nuclear model. And every once in a while, you see the term peach pit model. Imagine, if you will, if you cut a peach open, you got this big thing in the center, a big hard dense thing in the middle. That's the pit. That's kind of what we looked at. So here's the nucleus. Okay, I put the plus symbol because it's positively charged. Okay, it's small and it's dense. So what Rutherford believed is that rather than the mass being kind of distributed out among this big cookie, is that all the mass was squashed into the center of the nucleus. Well, where were the electrons? Well, Rutherford believed that they were still there, but they weren't in the nucleus, obviously, because the nucleus had positive charge. So they were just around it somewhere. Now this is the hard to believe thing that he stated. He said that the atom was mostly empty space. This is pretty hard for people to believe, okay? But Rutherford said, look, we know that there are electrons because the cathode ray experiment showed very clearly that there were tiny negatively charged particles that could be ejected out of the atom. Okay, the gold foil experiment shows pretty clearly that there has to be something that's tiny and dense and positively charged, and that's in the center. It can't be anywhere else because it's very small, because most of the alpha rays, alpha particles, just went right through. Some of them came close enough. Okay, so here's my alpha particle. It's doodling along here. Okay, and it just goes right through. It doesn't get changed because there's nothing there. These are so tiny, okay, they don't really have any impact on it, okay? Sometimes some of them get here, and because they're negatively charged, they get deflected. Okay, and then every once in a while, you get one that hits the nucleus and bounces back off. So the atom has to be mostly empty space. It's the only way to explain what happened with the gold foil experiment. Okay, so how big is the nucleus compared? The nucleus, okay, is about, okay, let's say the whole atom is 1,000 times the diameter of the nucleus. So if we said the diameter was 1, this whole thing would have to be 1,000. Okay? So in other words, okay, the size of the atom compared to the nucleus is really massive. It's hard to draw that. It's hard to draw that to scale. Okay, so we just simply draw it this way instead. Now, your responsibility is you're going to have to know each of these three models. Who's the person they go with? What are they called? You're going to have to be able to draw them, and you're going to have to label them completely clearly. You do not have to draw alpha particles in Rutherford's model. I just put them in so that you can see how his model went along with the results of his gold foil experiment.